Hi, welcome to this column design course. And in this course, we are going to study about designing of tall cylindrical columns and towers. Okay. The columns are generally self-supported nowadays. They are supported either on cylindrical skirt or conical skirt. So designing of this tall towers is based on cantilever theory. Okay. Hope you remember cantilever theory. We can get equations for if it is loaded at one end or there is uniformly supported when uniformly loaded force is there. So for this, if you have forgot the equations about deviations and stress, the bending stress formula, we used to derive it also. So if you have forgot that, I'll request you to go to that chapter, try to just recall all those equations. Okay, that will be much easier for you if we move next forward. Okay, so this is the cantilever theory on which all the designing of this column tower is based. Okay. Earlier, the towers used to be guy wire supported, like you see here. But nowadays, the simply supported, columns are more preferred because your guy wire supported columns will require lots of space. Space is really a constraint in a power plant. Guy wire supported design is still preferred for stacks who are located at the corner point of a plant. We by guideline also we have to maintain some distance, so we have space also available for that. So we prefer guy wire supported for stacks, but for column, the process columns, we always go for simply supported. Okay. Now we'll just try to focus on what are the difference which may be there for a designing of column rather than designing a pressure vessels. Have you seen any clause in ASME which talks about column and pressure vessels, the difference between design? No, you will not find anything. Okay, so the basis of designing of pressure vessels and column remains same. The only thing which is very important is the application of these loads, how the loads will be applied. So code will say you have to apply all the loads which are applicable and then find out the stresses. But now how those some loads become really important for a column design. Okay, that is what we are going to see in this chapter. So we'll move to the next section where we'll see the detailed syllabus what we are going to cover. Okay. So this whole column design chapter has been divided into two main parts. One is theory and second is PVElite software training. Okay. So in theory, we are going to cover stress calculation due to pressure and dead weight. We are also going to see wind and seismic, how the stresses are created. Then we'll see the load combination of these pressure, then dead weight, wind or seismic, whoever is governing. Based on those, we will be calculating the thickness of column. Okay. Then we'll see axial buckling of a column. We'll see design of column with two or more diameter. Many times, like we saw in the earlier figure, the column was having two different diameters. So we are going to see the design of those kind of columns also, what additional things we need to perform. Then we'll see unity check calculation for a column, girth flange design, the flange which is coming in between the two shells of a column. Okay, whatever maybe the reason, maybe they want to separate the columns, So if a girth flange is coming in between, then what additionally we have to perform? What kind of additional data we need to add for flange design? Then we'll see wind induced deflection. We'll also see wind induced vibration happening in the column. We'll also see different types of support which we can provide, how to select the type of support. And then mainly we use skirt support. So if skirt supported, how the skirt will be designed for operating condition, how it will be designed for test condition. Okay. And then the attachment of skirt with head, that is also very critical weld. So how to design that, we'll see that also. Then we'll see the design of skirt base plate, also the top plate, the cleats which are coming maybe to support the piping or the platform which is there on the column. So this, due to this cleat, the loads of the platform or piping will be transferred to the column main shell. It need to be addressed. We have to check that WRC calculation is performed. We are going to see that how we will do that calculation. Then we'll also discuss about hot box. What is the hot box and how to take care of that. Then we'll move to the second part, which is PVElite software training related to column design. So we'll model complete column with different shell segments because we have to optimize the shell thicknesses. Skirt will model completely with skirt and all the design loads like wind and seismic, everything will insert, and then girth flange design. We'll also design a trunnion, which will be required for lifting up this column, and then tray, if it is coming in the column, how that should be modeled. WRC calculation for cleat support. Okay. So this is mainly what we are going to see about column design chapter in theory and in the PVElite software training. Okay. So now we'll move to first section, which is theory part. Okay. So in theory, now let us try to recap what we have studied in a pressure vessel. So generally what we did for internal pressure, which is acting on the pressure vessel, there are two different types of stresses which are generated. Okay. One is circumferential stress and other is longitudinal stress. Okay. We know that circumferential stress are calculated by PD by 2T. Longitudinals are calculated by PD by 4T. So we know that circumferential stresses are twice more than longitudinal. And that is the reason the thickness calculation is always governed by circumferential stress. These are the formula given in code. So when I say code, actually I mean ASME section 8 division 1, because that is the area of focus, okay, for us, this chapter. The right hand side is the formula for stress calculation, code formula for longitudinal stress. Okay. So now earlier for pressure vessel, or most of the time your circumferential stresses will be governing the design. But now in column, there are some additional loads which may be governing the stress or may be contributing to the stress in the longitudinal direction. Right now we have only pressure, and due to pressure, we have this PD by 4T stress. If we just talk about academic formula, there will be some loads which will create additional stresses for the pressure vessel. Can you think of such loads which will create stresses in longitudinal direction? Okay. Think of it. If you have thought up, try to make note of it. Okay. And before going to the next chapter, you should have few loads. Okay. And then we can check whether you were right or wrong. Okay. Now let us move forward to see what are these loads. First is dead weight. Okay. We are going to see the stress calculation. Okay. So don't worry about that. We'll elaborate this process of stress calculation for dead weight. Next is wind load. Wind load will also create stress, which is additional and in the same direction in the longitudinal, okay, or seismic. Okay. So either wind or seismic will be taking for the case. So all these three loads contribute stresses in longitudinal direction. Okay. So now if additional longitudinal stresses are coming, then you know that now the longitudinal stress, which was half earlier, now it will increase. Okay. It may happen that it may go even higher than your circumferential stress. If that is the case, then your longitudinal stress will start governing the thickness calculation. Okay? That is where your column design is different. Now let us see the calculation of stresses due to all different loads which we just saw, like dead weight, wind, and seismic. There are other loads also, but these are the main loads which we are going to consider. And we are going to see how the load combination is done, how it is compared with allowable stress. Okay, there's a very trick there when we compare it. So, be there till the end of this video, and you will know how this combination is done. Okay, so now if you're talking about dead weight will be maximum at the lowest section of the vertical column. Okay, we can see here the column. So at the bottommost part of this column, the dead weight will be maximum. So the stress also will be maximum. How we'll calculate the stress? If we just take the cross section of this column, these are the weights which is coming on that area. Okay, which the cross section which we can see. We can calculate stress. Simple. Force divided by area. W is the total weight, which is the force. We can convert that into Newton, divided by pi dt. Here we have made one assumption that your thickness is very small compared to the diameter. So with that, your area calculation will be pi dt. So this will give us a stress which is acting in the longitudinal direction. Okay. But now the catch here is that it is a compressive load. Okay. It's a compressive stress. Now, how the compressive and tensiles are different. See, due to the pressure, the longitudinal stress which was generated, it is tensile in nature. If you see in the figure, this is the figure for tensile stress. It will try to separate the two objects, while compressive will try to match them, try to compress. Okay. It is compressive in nature. It will try to push, okay, not pull. Okay, so I think by looking at this figure, more or less, it will be pretty clear to you what is compressive and what is tensile stress. Okay, and okay, so the longitudinal stresses due to pressure, we know that it's tensile in nature. Okay, so we'll cut here. Okay. And I want you to take your time and try to digest this theory. Okay. The concept of compressive and tensile, if you have understood, then that will be really helpful, because there are other loads which also we have to calculate the stresses, and we have to do the combination. In that, it's very important whether load is tensile or it is compressive. We have to see that. Okay. So okay. So now we'll go to wind and seismic. So we will take first seismic. So in wind or seismic, we take only one of these conditions, whoever is governing, because the chances of occurring both of these is very rare. Okay, now if that happens, it will be really catastrophic and nothing will remain. So there is no point in trying to design my equipment for that. There may be the chances that no life will remain there if both of it come together. Okay, and if try to do that, and if I try to design my equipment for that, it will be too conservative and too costly. So we don't have to consider both of these acting together. So we'll take one. We'll see how to calculate the stresses by both of these, but it will be only one who will be giving the maximum stress. Okay, so we'll take only one. Okay, so first we'll talk about seismic. So If you remember, seismic is nothing but an acceleration. Okay, acceleration generated. So when we multiply this acceleration with the mass on which it is getting applied, in this case, it's the mass of the column, it will be acting in operating conditions. So liquid weight also will be added. So total weight multiplied with the acceleration will get the force. This force will be acting at the center of gravity. Now, the center of gravity location multiplied with this force will give us moment. Now, once we have this moment, we can use the stress formula, the cantilever theory. If you remember, stress is m by z, moment divided by section modulus. Section modulus is property of your section. Okay, so in this case, it will be pi r square into t for this shell. So moment multiplied with divided by section modulus, we get the stress, which is bending stress. Okay, so if you remember, bending stress is always occurs in pair. It will be positive one side, which we can call it as tensile stress, and negative on the other side, which we call it as compressive stress. So it will be tensile one side, compressive one side. Okay, so pressure is tensile at all the point, deadweight is compressive at all the points, seismic is tensile at one point and opposite point will be compressive. Okay, you can see the difference. Great. Now let us talk about wind. Okay. So when wind flows, due to the velocity of wind, we can calculate the wind pressure. Okay, this is the formula for wind pressure. It's an academic formula. If you apply code, there are lots of additional factors which will be coming into the picture when you calculate the wind pressure. Okay, now this wind pressure multiplied with the cross sectional area of this column will give us the force. Okay, this force again I'll apply at the centroid, the center of this area of this column. It will give us moment, and if once I have the moment, stress, same formula, m by z section modulus, we get the bending stress. Again, similarly, like we saw in seismic, there will be positive one side, and so at windward side where that wind is coming from, that side it will be positive. At the leeward side, it will be compressive, so negative. Okay. Okay, so we have seen load calculation due to pressure, due to weight, due to wind and seismic. Let us study the combination of these. How to do the combination. Okay. So for combination, we are just considering wind. If seismic is governing, you can take seismic. Okay. So for wind, from where the wind is flowing, that is windward side, opposite is leeward side. So for windward side, the stress generated by pressure can be given by this formula. You can see the positive sign here. This indicates the tensile nature of the longitudinal stress due to pressure. This will be added with the stress getting generated due to deadweight. Now the deadweight being compressive in nature, we see here negative sign. Okay, that will be added with the bending stress. So if you remember, this is the side where tensile stress will be governing. So bending stress, which we get as positive in nature. Okay. Now, same thing for leeward side. Only difference is that bending stress due to wind will be negative because it's compressive in the leeward side. Okay, great. So we have load combination at windward side. We have load combination at leeward side. Now, if we add these, this will give us the total stress. Okay, and mostly that total stress in the windward side will be tensile in nature, and the total stress in leeward side will be compressive in nature. Now, once we have the stresses, how we get the thickness? So for that, for windward side, all the summation of these stresses is compared with the code allowable stresses. Okay, because total stress generated should be lower than what is allowable by code. Okay. Similarly, for leeward side, total stress should be lower than code allowable stress. But here is the trick. Here is the most important part, that code ASME section 8 division 1 as per UG 23D, if earthquake or a wind are considered in the combination of loading, we get to increase the allowable stress by 20%. Okay. So in this case, my allowable stress will be 20% more. Okay. So my allowable stress in this case is going to be 20% more than the stress which we use for pressure calculation, because wind or seismic, if they are appearing there. Okay. Now you have to think how or why we can permit allowable stress more than my normal stress. How I can go up to 20% higher for this combination of loading? What may be the reason? Okay. So I'll leave you to think of that point. We are going to discuss that. And if you remember the chapter which we covered in the start about different types of stresses, okay, primary and secondary, and the allowable of it. So that is a kind of hint, okay, through which you can come out that how code can allow more stresses for wind or seismic. Okay, great. So this is the basic philosophy behind the thickness calculations of column shell. So little different than your pressure vessel design. There are some additional loads which become really critical here. So thickness may govern by longitudinal stress. Okay. Now, apart from this, do you think any other kind of load also may be there which may govern the thickness calculation? I want you to think of any other mode of failure which your column may see. Okay, I want you to think about it, and then you move to the next section. This is the end of part 1, and I hope you guys learned something, clarified few concepts. Okay. In the next part, we are going to see designing of column against buckling. It's very important concept. And then we are also going to discuss about the designing of column which is having 2 or more diameters, okay, like we saw in the figure. Then we are also going to talk about deflection calculation for a tall tower and wind induced vibrations. Okay, so see you in part 2.